The speed of light in vacuum, commonly denoted c, is a universal physical constant that is important in many areas of physics. The speed of light c is approximately 300,000 kilometers per second. All forms of electromagnetic radiation, including visible light, travel at the speed of light. For many practical purposes, light and other electromagnetic waves will appear to propagate instantaneously, but for long distances and very sensitive measurements, their finite speed has noticeable effects. Starlight viewed on Earth left the stars many years ago, allowing humans to study the history of the universe by viewing distant objects. When communicating with distant space probes, it can take minutes to hours for signals to travel from Earth to the spacecraft and vice versa. In computing, the speed of light fixes the ultimate minimum communication delay between computers to computer memory and within a CPU. The speed of light can be used in time-of-flight measurements to measure large distances to extremely high precision. When we discuss the constant c of c, we mean the speed of light in a vacuum. Since interstellar space is very empty and much like a vacuum, astronomers usually don't have to consider the speed of light in different media. However, the speed of light is not constant as it moves from medium to medium. When light enters a denser medium, like from air to glass, the speed and wavelength of the light wave decrease while the frequency stays the same. How much light slows down depends on the new medium's index of refraction n. The speed of light in a medium with index n is c divided by n. The index of refraction is determined by the electric and magnetic properties of the medium. For air, n is 1.0003, for ice, n is 1.31, and for diamond, n is 2.417. For visible light, the refractive index of glass is typically around 1.5, meaning that light in glass travels at c divided by 1.5, approximately equal to 200,000 kilometers per second. The refractive index of air for visible light is about 1.0003, so the speed of light in air is about 90 kilometers per second slower than c. Light moves slower through denser media because more particles get in its way. Each time the light bumps into a particle of the medium, the light gets absorbed, which causes the particle to vibrate a little, and then the light gets re-emitted. This process causes a time delay in the light's movement, so the more particles there are, the more dense the medium, then the more the light will be slowed down. Einstein's crucial breakthrough about the nature of light, made in 1905, can be summed up in a deceptively simple statement. The speed of light is constant. So what does this sentence really mean? Surprisingly, the answer has nothing to do with the actual speed of light. Instead, Einstein had an unexpected and a paradoxical insight that light from a moving source has the same velocity as light from a stationary source. For example, beams of light from a lighthouse, from a speeding car's headlights, and from the lights on a supersonic jet all travel at a constant rate as measured by all observers, despite differences in how fast the sources of these beams move. The special theory of relativity is based on Einstein's recognition that the speed of light does not change even when the source of the light moves. Although it might seem logical to add the speed of the light source and the speed of the light beam to determine the total speed, light does not work this way. No matter how fast Einstein rides his bike, the light coming from his headlight always moves at the same speed. Light from a stationary source travels at 300,000 kilometers per second. Light from a moving source also travels at 300,000 kilometers per second. Say that Einstein's bike travels at 10% of the speed of light, that is 30,000 kilometers per second. The speed of light from Einstein's headlight does not equal to 330,000 kilometers per second. The speed of light is constant and does not depend on the speed of the light source. It only varies based on the medium.